So welcome back to Python. Oh, today so many students, very good. Yeah, much more than last time. Right. So last time we, we stopped here plotting. We had a function, something similar to a Lorentzian, with a small shoulder near or just below x equals 4. Right. So basically here is the small shoulder. And we had a look into adding an inset into our graph to highlight details, right? We had vertical lines added to indicate the inset region and then enlarged that part of the graph. With this, we already close or have completed the one-dimensional plots. Right? So f is a function of x. Now, most of you are material scientists, and when you see a TEM or SEM image, what do you see? You know, TEM, SEM, transmission electron microscope, scanning electron microscope. We also have backscattering. So here the battery are ending. Take this one. What do you see normally? Well, in image, right? I see a function of x and y. So we have to go to two-dimensional plots, right? Or plots, contour plots, however you will call this, where we again have a coordinate system, but this time we span the space over different points in space, and each point we give a value. You see an example here. By the way, the live stream is working or not this time? Maybe working. Okay, so here, right? This is a simulated image of some sort. You could maybe understand the green regions as electronic cloud from a chlorine atom. You can see interpret the brighter regions as electronic cloud maybe of sodium ions. And then what could be shown here could be an TEM or SEM image or scanning STM image of sodium chloride. Right, very simple. Basically, FCC with the sodium chloride crystal structure, right? Okay, this is again an image, right? So material science often use imaging techniques to characterize materials. For me, that's a function, and each point is a number, and we can interpret then the numbers of different kinds of informations. So what we're going to learn here is to generate images like this and to properly label them to have all relevant information. So let's start from the top. So what we're going to use is a few functions: imshow, contour, and contour f for contour filling. Imshow we already have encountered before. That was the function I wanted to use you in the exam, if you remember. I asked you to plot, but the only plotting function I gave you is imshow. So here, that one was supposed to be used. But we come to this at a later point. So what do we do? So in image show, we use a method where basically a 2D array is spanned over a regular grid. Were used. It's slow. Okay, so then at every point in space, we address a value on a color scale. Right, so without this scale. Let me see if it works now. So without that scale, what is that image? Give it a moment. The laptop is still tired, working very hard. Is that power on here? No, it's on. So without that scale, it's just an image. Right? So there's little signs there because I don't know what the values refer to. If the green region is a high value or if the whitish region is a high value. Almost there. So like this. Right? Can you tell me if the white region or the green region or the blue region has a maximum or minimum or what is it? No, you cannot. What you need to provide important in these 2D images is a scale. If you don't know the exact values because you're missing normalization, then you just put maximum, minimum. But you need to tell me what is what. Okay, and with this color scale, we finally can identify maxima and minima. Now let's take a look a little bit closer into that code. So here we implement a function, lambda, or through the lambda keyword, we provide two arguments, m and n, and then m and n are used in a sine function and a cosine function respectively. M and n are independent. So I can choose one n and I can have very, very different sets of n, right? I can choose one n and I can have very different n. So here my m and n are basically directions in a grid. M, for example, this direction and n this direction. So what we have then, if we pick one value for m, we just go through different values of the sine function. That means we go from maxima to 0, to minima, to 0, to maxima, and so on. So if I go along this direction, I should see, well, a period, which I do, right? You see, we have many different maxima and minima. And the same applies for the cosine function in the other direction. Minima, maxima, minima, maxima. Now, there are parts that are always blue, right? There are parts that are in between minima and maxima. But if you remember, the sine function goes from 1 to 0 to minus 1. Now, when you have here a value of 0, right, you go, what is a minus 1, 0, 1? Here you stop at 0, now you go this direction for different m's. So whatever you take in this composite function, where we take the product of sine and cosine, we always will get 0, right? Because anything times 0 is 0. So in these regions, right, if we go one direction or the other, it stays 0. And this is a very important part. So what else can we do? So in line 4, we basically collect the values in a matrix form, an array, with the from function, where we provide the implemented lambda function in array, 630-ish times 630. And we say it's a float type. In line 5, we then provide the matrix with the data to the imshow method. And lastly, we add the scale here on the side, as I showed you already. Now, there are a few things I want to show you as well, since you're already here. Right, why not? So I mentioned there's a sine and cosine function hidden somewhere. So if I use PLT, let's say scatter, I need x and y. and I choose one particular direction. So I choose one axis, all values, first entry, and I provide a grid on the x direction, 0 to 6, can be 1, let's say 10, 6 to 8. Then I should be able, so this one doesn't make sense here. No, because it's always 0, right? I change to the next one. I see a small cosine popping out. You see that? I basically selected one axis. First selection, I was unlucky, I selected this point, then everything is 0, right? But when I now go to select several values, we actually see that with increasing index I in the matrix A2, I will see that the cosine functions basically are going to increase. Okay, so far so good. And we start at 0, and then the first cosine function is small, the next one is larger, it's larger, larger. Because in this 2D map here, right, we start at 0 and we approach slice by slice the line here with a maximum. So far, so good. Difficult, easy. Make an array, plug it in, imshow, right? A lambda function we talked about, from function we talked about. In principle, nothing too new. Okay, so now making the plot proper. I mentioned before that when you give me a plot, I want to see axes, I want to see labels, units, no improper use of white space, and a few other things. So go back up here. We see, for example, there are no labels. So while I also expect that could be a STM image of a simulated STM image of sodium chloride, I now go down to actually make proper X and Y labels. So here in this plot, in contrast, you see the m-axis is now labeled as y and the n-axis labeled as x. Plus my scale has a label too that says intensity. How do I get this? So here the syntax or the commands are a little bit more involved. So in line 1, we again asked for an axis and a figure object from subplots. In line 2, we asked for the plot. Right? So here is x. Is it okay? X in show and then the command we have done before. But please take note, there is plot image at catching the return value of this plot here. Right? Go above. Scroll up, scroll up, scroll up. Over here in line 5, we just call the function. But when we call the function, we get a plot and we get a return value. And the return value is the handle to the plot. So image plot is catching some information. Plot image catching some information from the im-show method. In line 3 and 4, I set the x labels, right? Nothing too new, we have done that before. Set x label, set y label. Now in line 5, I call a new function, right? The function, however, is on the figure object. it's not on the axis object, it's on the figure object. Remember, we have a figure object, and the figure object contains the axis object where our plot is inside. And I call the color bar, and I pass the handle to the axis object, which contains my 2D matrix represented by the inShow method. And I again catch a return value. Right? And this time the return value is for the scale here. And then I can take that object containing access to the scale and say, add a label. So this is a 3-step process, right? Make in image in an axis object, catch the value, right? Catch the access to that object. Then add a scale containing the information of the axis object into the figure object. And lastly, take the access to the scale object and add a label. 1, 2, 3. Okay. As I remember, when I was preparing this, the order is very important. If I, for example, exchange figure here for a scale to the axis object, let's see what happens. Oh no, I don't have a color bar, right? So that suddenly is not accessible anymore. Above here, it's different. We use PLT. Let's see if we can use PLT. Also works, right? Fine, can we now change, for example, C bar, right, our color bar, to axis object? It doesn't complain, but I don't get the label. Okay? Because that axis object, well, I'm actually not really sure where the label goes, but it's not displayed. When I want to have my labels here on the scale, I need to find the right object to put it on. Let's try figure. Set label to a figure. Interesting. Also don't see. So use the right objects. So I put this back to figure because this is the way I do it. So far, so good. Again, 3 steps you have to do. And you basically only have one choice over here to either use dot or figure, the rest you need to keep in order. So that the information is probably passed from object to object and placed at the right position in the plot. Okay, but basically something to note down, something to put somewhere, and to look up if you really need it. But without proper labels, things are not done properly. Okay, so now contour F. Have you ever used a map? Do you like to go hiking? Or diving? Flying? Airplanes? Well, I know in Taiwan you have this, what was it? The sailing, flying? How do you call this? The airplanes that don't have an engine? It's sailing planes. You just pull them up very fast on the ground and then they fly and glide. You have that somewhere at Maolin, right? There's a flying place. Anyhow, you also have a lot of mountains. So whatever you do, you need to know how high the mountain is. So you open a map. Even Google Map has this, right? And then Google Map, there's some way to look at the terrain to see the height, right? And then there are funny lines or regions, and sometimes they have a number on them. 30 meter, 40 meter, 60 meter, right? That is the contour map. So how does the contour map works? Well, the contour map gives you values at intersections between different contours, and then intervals where these contours are valid. For example, from 30 to 40 meter. And then you have a new contour from 40 to 50 meter. So why would you do that? It simplifies plots. Right? It makes them maybe easier to estimate where certain values are. Right? How steep is your mountain? Okay, we can do the same with our data. I quickly change. You know what? I don't change anything here. You can change if you like to do the same plot or with the same data with image show. Instead, we're going to talk about the plot, right? Line by line again. So in line 5, yes, in line 1, I create an array X containing the values from -5 to 5 and step sizes of 0.1. So that is quite a few values, and I do the same with Y. Then I call a new function called mesh grid. Now the mesh grid method, I have that somewhere? No, I thought I had that. So the mesh grid method works like this. Draw. Can I draw here? So let's suppose we have two axes defined are given by an area, right? For example, x and y. You can see what I do, right? Okay. Now the area I just created started -5 to +5, right? With a lot of values in between. That is one area. Right? It's one independent area, so it's one direction. I did the same for y area. Starting at -5, going to 5, with a lot of values in between. So now I can call a function on the data on x and the data on y. But to create a two-dimensional area, right, a two-dimensional grid that gives me access to every point in this space spanned by x and y, I basically need to take the tool axis, right? Choose another color. This color over is good to explain, right? And then I say over here, for example, maybe I have coordinate, what was it? X equal maybe 2 and y equal 4, right? But then for every x, I have many different y's. Okay, so I need to take this whole axis here, right, and apply it also here to get a grid space that is available for all points for this particular x. And again, I need to do this for all my x, right? And then I need to do the same thing for all my y values, right? Putting the x-axis through all these points, and I would have a grid in 2D defined in two vectors in 1D. And that is exactly what now the mesh grid function is doing. Okay, so I have here my 2D function. Let's investigate this a little bit more, because one part is me explaining things, which is, of course, always very successful. And the other part is actually me demonstrating things, which make things a little bit easier. So I reduce now the grid size, right? I go from -1 to 1 in steps of 0.5. Let's first look into x and y. Right, so that is one of the things we normally do the moment we face some complicated code. We explore things step by step. you can take a code apart, and when you understand each line, you can understand the entire code. So here, now I have two vectors, right? So this is x, 4 values, and this is y. So far, so good. They are still independent vectors. If I now would say find them in mesh grid, so I take one vector and I take the other vector, at every point at one vector apply the other vector, I will get a 2 by 2 matrix. Let me try this to show you. Over here. Right, so now I have repeated the x value for every position of y. These were the green lines. And I can do the very same thing for every position of x. Right, so we have here constant values in x, right? We start off -1 for potentially different y's, minus 0.5, 0.5, and for the y part, we have same constant values but in the other direction. But this is actually exactly how a grid works, because when I more colors, so if here selected, for example, the value of x equal 2, right? If I go down this direction, for example, picking this point, x is still 2, but now the y value is made -3. Right? If I shift my x position, x is different. If I go along that x, up and down, x doesn't change, y does. Now what I need to do to define the entire grid is making use of both grid information, right? One for the x component, that's xx, and one for the y components, that's yy. So far, so good. So mesh grid helps me to create a regular sized grid with an x component and the y component that I can catch separately. Now there's an argument bars. If we have very large grids, then things can be efficiently handled through some sparse matrix algorithms, which I here don't introduce because it will make things easier to, more difficult to understand. Of course, I would have introduced it if it would be more easy, right? Okay. Anyhow, so now with these grids, right, we have access to x and y components of the grid, and we can use the implicit vectorization of NumPy in its functions, right? The element-wise operation on the sine and cosine functions. Anyhow, so in line 3, I use the grid, I pass them to a sine function, and I pass them to just an addition. So when you see here x squared plus y squared, what do you think it is? 2D data, things look round things, you use polar or spherical coordinates. So x squared plus y squared is probably r squared, right? Okay, and then we have sine r squared divided by r squared. So far, so good. So this function you should have seen before in the form of sine x squared divided by x squared. It's a very common function. If you like, you can go up, modify the code here a little bit, get that, or we look at it later together. Anyhow, so we store the z information, so the height value of every point on the grid in x and y and z. And then we ask z, hey, use your x and y components to plot the z value. Let's see if this is still working. Yes, beautifully. Yes, no, maybe. Let's try something. Let's look into Z. Right, so Z here is a two-dimensional array. And in principle, I should be able to plug it into imshow. Beautiful. No? Yes? Maybe. So in imshow, we display the actual value of each point of this two-dimensional grid, here represented now by the height information stored in Z. But in the contour F, we have a different form of access to information, right? But in principle, the data shown are the same. Again, we need to add labels and axis and scale. Now, the scale we have here, we have the intensity label, we have x and y term of a position. It would be nice if you add units the moment you can. What you should note is the intensity scale is not centered at 0. Right? So this is actually fixable if you really have to make things align properly. We come later to this. Now, right. I also said we're going to look into the contour function, right? Not contour F, F for filling, just contour. So you move the F. Looks a little bit different because we will just see the lines, right, without the filling. This is actually nice if you need to overlay information. Let's see what we can do. If we can do it, let's go here, copy the color map. Then we go here, insert over here, x.in show, what called Z color map. Let's see. Two commas don't work. That's right. Right. So over here now I have. Let me see. I snap the alignment. I can't. I scroll down. But in principle, it's possible to overlay two plots. Right? So here is the contour plot, and here is the image. So if we put a little bit of effort from here to proper alignment, we could do this now. Let me think if I can quickly fix this. Mm-hmm. Check. This is 0 to 80. That is what? From -5 to 5, right? Yes. So what we need to do is we need to add 5, and then we need to scale it a little bit. So we spend 10, 80, so times 8. So if this works, it's great. If not, we just continue. I think there should be a minus as well. Well, almost, right? So you can fiddle around a little bit more to get the proper alignment by scaling and shifting the axis. 80, probably 90. So that allows you, for example, to build a model in the computer and overlay with experimental data. Almost, right? So what am I doing wrong? 80? It's not stopping at 80, it's stopping at 110, right? What do I set 80? It's like 5 and 5. Now I messed up. 80, 80. We have 10 in the additional array. Overshot a little. So here's the thing, right? If you talk and think, it's a little bit difficult. Here we go. Beautiful. Oh, yes, no? So your STM images are in gray, right? So you can put some color over them if you like. Possible, right? Control your data, control your plot. Don't change the content of your data, but you're allowed to process them, right? To make things visible you want to highlight. But if things are not there, right, if you put them there, that is misconduct. Good. Are there questions to 2D plots? Easy, right? Everything is just a 2D array and then im show contour f and you're good to go. Right. So there's actually more to this. We have only talked about irregular data. Sometimes our grids are irregular, so that needs to be addressed at some point as well. But for regular grids, you know what you could do. Next, we go to three-dimensional plots. So three-dimensional plots are fun to look at. But three-dimensional plots are a little bit hard to read off values because parts of the plot can hide other parts of the plot. So whenever you think about making a three-dimensional plot to add into your scientific presentation or thesis or wherever you want to put it, consider careful if you have to do a 3D plot and what is the added value over a two-dimensional plot. Maybe there's a better way of having one or more two-dimensional plots instead of having one three-dimensional plot. So we proceed very, very similarly in the three-dimensional plots, going to the from the two-dimensional plots to the three-dimensional plots. What we need to have is first data to produce and then present it. Now, I would say that there are there are a few different types of three-dimensional plots. One is basically a two-dimensional contour where the height information is given as color but as literal height in the 3D plot. Similar to you having a map of a mountain, right, with the contours of the height, versus having a three-dimensional model of that mountain. So you see here already, I again define x and y in a linspace method, and then I define a grid using x and y. This I call the grid capital X and capital Y. And lastly, I provide the height information or the Z information through that grid information stored capital X and capital Y. And then I create a figure and axis object, do the subplot routine again. I explicitly ask Python in line 2 to get my scale aligned symmetrically around 0. So how do I do this? From the matplotlib package, I ask colors normalize, and here I tell Python take the absolute value of my height information stored in Z, so this absolute value. So all negative becomes positive, and positive maintain positive values. Find the maximum. So if my maximum is 10, it stays 10. If the absolute value is found to be biggest in the negative, for example, minus 20. Minus 20 becomes to the absolute function 20, and I still have the maximum here. And then I say, oh, take the negative of this value. So it becomes minus 20 again. And in the normalization, this would then be the lower bound. I do the same, right? In the absolute, looking for maximum, but providing the information as maximum. So if the largest value in absolute terms is really minus 20, this function reads minus 20 and plus 20. But that is then symmetric around 0. Because A and B, right, the beginning and end of the interval, have the same distance from 0. Okay, and that I say, oh, this is my normalized color bar here. Okay. Or the norm, right? And then I have a pcolor function where I provide x, y, and z. It has basically the appearance of imshow, but the syntax of control-f. I can provide the norm information from line 2, and I choose a color map here. BWR is blue, white, red, meaning I have blue at the minimum, I have white in the middle, I have red on top, and then I basically already have main parts of that plot. Let's see. So I need to run the grid here. MPL not found because I didn't import it back. So just do that. Import MPL, very good. Okay, so you see it's there. Now we want to add the scale again. There we are. Wait a little bit. Right? And the parts I just pasted back in, again, are the axis labels and the scale label. What I want to show you next is we remove the norm from the code. So why can we do this? By the way, this looks funny here, right? This looks red, bluish. On my screen, this is just blue. So the function itself, again, has parsings through 0 that reveal a regular grid within the data, right? So we go again from maxima to minima to maxima and so on. If I don't apply the norm now, it will be harder to tell if the grid and the maxima and minima are aligned at 0, or if there is a constant shift in one or the other direction. Here, for example, the white region is still visible, right? But the parsings indicate that maxima and minima are shifted more towards the side of the maxima, right? So you would need to read the scale very, very carefully. Find this color, right? And then, oh yeah, my zeros are here. My zeros are here. Okay. So why is it, by the way, important to talk about zeros so much? Well, numerically finding solutions of problems often identifies with finding the crossing between plus and minus, right? The zero position. It's one way of doing this. Putting back the norm will help us to, for example, find graphical solutions more easily. On the other hand, it's a more proper representation of the data because we have here a decaying function that again we see through a factor that is basically a Gaussian. Okay, so far so good. Do you want a break? Okay, break time.